Welcome back for final talk of today. So final speaker will be Dr. Raja Swaminathan, who's Senior Fellow at AMD. He's responsible for package architecture and advanced technology and strategy and development. He has been a package architect at Intel for 13 years, then moved to Apple to architect the new silicon package architectures before moving to AMD to drive the industry-leading chiplet architecture integration. He received his bachelor's from the IIT in Madras, did his PhD at Carnegie Mellon University. He has over 35 US patents in the field, and he's an IEEE senior member. And in his talk today, he will show us how we can enable Moore's Law's next frontier through heterogeneous integration.
Good evening and good morning to the ThoughtWorks attendees around the world. Really appreciate and thank the ThoughtWorks conference for inviting me to present our view on how advanced packaging will enable the next generation of Moore's Law scaling through the use of novel heterogeneous integration architectures. As has been widely documented and discussed even during the previous talk, Moore's Law is slowing down, and the cost per yielded millimeter square of silicon area keeps increasing with node progression, as illustrated by the slope of the curve changing around N7. In parallel, die sizes for high-performance computing are also growing rapidly beyond reticle size limits. The bottom left chart shows die sizes of server CPU in blue and GPUs in red, and they're approaching reticle limits already. And the breakdown of Dennard's law, means power for high performance computing also keeps increasing. The bottom right graph shows power of top 100 supercomputers in the world, increasing from 1 megawatt to about 10 megawatts in less than a decade. All of these challenges are coming in at an exponential rate to keep pace with the insatiable demand for computing, especially in the high-performance computing markets. Let me just move my Zoom screen to the other screen so it's not impeding your view. So compute demand is increasing, but needs to overcome significant barriers to traditional Moore's and Dennard's law scaling, once again illustrated by the server CPU and GPU die sizes over the last decade. The second chart in the middle illustrates the bits per year projected for CPU and the CPU-GPU markets, and is also growing at unsustainable rates, driving the need for domain-specific accelerators. Accelerators can deliver more performance within the given power budget, cost, and other constraints, but leads to potential new complexities for highly accelerated, highly heterogeneous systems. Every system architect is going to solve different problems using different data, different end product requirements, and industry drivers, which brings us to the future of computing as being defined by modular designs driven by the era of advanced packaging. A quick background on chiplets. Historically, Moore's law enabled sufficient scaling to satisfy computing demands, except for very large systems. So we were able to design a piece of silicon and then put two of them together to get 2x of performance, approximately. But with Moore's law slowing down and the performance needs increasing at exponential rates, the traditional approach for growing die sizes, where area growth directly translates into performance gain, is not sustainable anymore. This requires a new approach with chiplet-based architectures to continue scaling for high-performance compute demands. But the challenges with chiplets are multifold. You have additional I/O area, additional design effort and complexity, as well as a requirement for new methodologies in design, test, assembly, and sort. The transition from monolithic to chiplet approaches is illustrated in this slide. The key value with chiplets is that they provide a scalable path to enable many more functional SoCs due to the ability to yield many more die in a given wafer. This is illustrated in the difference between the bottom of the slide, showing increased number of functional SoCs, versus the top of the slide showing reduced number of functional SoCs. Chiplet-based architecture also provides better known good die and ability to mix and match at finer granularity on the package. They also enable productization of the same die across different market segments, as demonstrated in the Zen 3 core compute chiplets being used across server and high-end desktop markets. Hence, modular designs can be seamlessly enabled with the use of chiplet-based architectures. AMD has been down the modular design path for many years now, enabling industry-first 2.5D HBM and multi-chip module, to enabling chiplets in the mainstream EPYC and Ryzen families, as well as our recent introduction of the 3D chiplet compute architecture at Computex. Modular designs with advanced packaging architectures need to focus on a few key parameters. First and foremost, the cost and volume manufacturing capability with scalable, cost-effective solutions. Second, bandwidth density at a minimal die-to-die interconnect overhead, as well as energy per bit to reduce die-to-die power. The key focus areas in silicon package core design and optimization are performance, power, area, and cost, or PPAC, PPAC for short. These determine the choice of the type of package architectures that can be paired with silicon nodes for specific product implementations. Chiplet-based package architecture definition is also more nuanced, since we need to figure out how to enable the best PPAC by using the right heterogeneous architectures for configurable segment-specific optimization, since not all products can be bound by the same PPAC requirements. The other goal is to maximize product yield by enabling smaller chiplets without significant interconnect overhead. Since with standard packaging techniques, I/O can consume a large area on the silicon, which can become extremely cost ineffective with silicon node scaling. AMD, in partnership with our ecosystem partners, are continually expanding our advanced packaging toolbox to enable our chiplet roadmap with tighter integration schemes to be able to scale into high volume markets. Many package architectures exist in the industry to enable die-to-die interconnectivity across various product segments, from mobile, PCs, servers, and desktops. Examples include MCM architectures from AMD and other industry players, other 2D architectures based on RDL-like interconnects, also known as 2D organic architectures, like InfoR and FOCOS, 2D silicon-based architectures, like Embedded Interconnect Bridge, EMIB, InfoLSI from TSMC, Silicon Interposer, as well as the other die-to-die interconnect architectures using passive silicon. There's also 3D architectures defined as active on active silicon stacking. Foveros, ODI from Intel, wafer-on-wafer architectures found in the image sensors and the memory markets. Chiplet architecture choice is not a one-size-fits-all approach. Rather, they're made based on specific PPAC requirements per product. "2D package architectures are typically less expensive than 2.5D and 3D architectures, while 3D architectures provide the best interconnect energy and bandwidth efficiency. So how do I find the optimal solution? Due to the challenges noted earlier, chiplet-based package architecture and definition requires balancing a complex trade-off. The value of the modular product being architected, plus the associated chiplet yield and technology scaling benefit, should be more than the I/O silicon area, the packaging cost adder, and the power cost of the interconnect, as well as cost of the engineering complexity of the resulting solution. Hence, this becomes a multidisciplinary optimization exercise across organizational boundaries. AMD's investments and innovations in packaging have been a multi-year, multi-technology journey. AMD introduced the high bandwidth memory and the 2.5D silicon interposer to the GPU markets in 2015, which led the industry for best memory bandwidth in a small form factor. We then set a new performance trajectory for compute in the data center and PC markets in 2017 with the introduction of multi-chip module packaging. In 2019, we introduced industry's first chiplet-based technology using different process nodes for cores and the I/O in the same package, which enabled significantly higher performance and capabilities. At Computex last year, our CEO, Dr. Lisa Su, announced the next big step in our continued trajectory in pushing the limits of advanced packaging, 3D chiplets that we've pioneered in close collaboration with our foundry partners. This architecture combines our chiplet packaging with die stacking to create a 3D chiplet architecture for future high-performance computing products. AMD's packaging roadmap is shown in the context of the IEEE heterogeneous integration roadmap metrics. The linear interconnect density on the left y-axis and the areal interconnect density on the right y-axis in logarithmic scale. These are metrics that the IEEE introduced a couple of years ago under the assumption that heterogeneous integration will be required to scale Moore's law further. Linear interconnect density refers to the number of interconnect wires per millimeter that can be escaped on the SoC edge, and is a good metric for 2.XD architectures, and is represented by the gray colored line. The scale goes from 1 to 1,000 wires per millimeter per layer. Areal interconnect densities refers to the number of wires per millimeter square of the SoC area, and is a direct function of interconnect pitch, and is a metric for both 2D and 3D architectures, represented by the orange colored line. The scale goes from 10 to 100,000 wires per millimeter square. Performance, power, and interconnect area typically scale moving from 2D to 2.5D to 3D architectures. With 2D MCMs used in our EPYC and Ryzen family, 2.5D and silicon interposer architectures for high bandwidth memory, and now the 3D chiplet-based architectures, AMD's advanced packaging roadmap now covers the entire interconnect density portfolio to enable high-performance computing products. Next, we get a little deeper into our 3D chiplet architecture. We are using an industry-first hybrid bond plus through silicon vias that provides over 200 times the interconnect density of 2D chiplets and more than 15 times the density compared to other 3D stacking solutions that are out in the market. This enables a much more efficient and denser integration of our IP blocks. The die-to-die interface is using a direct copper-to-copper bond with no solder bumps of any kind. This approach dramatically improves transistor density and the interconnect pitch over other 3D approaches, and is the most flexible active-on-active silicon stacking technology in the world. With the tiny through-silicon vias and the direct copper-to-copper bonds, this technology consumes less than 1/3 the energy per signal of the microbump approaches. This is a truly revolutionary technology that is a key part of how AMD will push the envelope in high-performance computing over the coming years. Next, we deep into the die floor plan over the SRAM region indicated by the purple area, where the TSPs are inserted to illustrate the interconnect density differences between a standard 2D MCM or C4, 3D microbump, and TSV-based architectures. In the upcoming video, I encourage you to focus on the purple swath and pay attention to both a dot and the hypothetical effect to the swath. You will see the impact of enabling a hypothetical C4 and microbump architectures followed by our implementation of the through-silicon vias. If you had enabled the 2 terabytes per second SRAM bandwidth between the SRAM and the core compute devices with standard C4-based interconnects, it would spent a lot of silicon area, as you can see in the huge swath of purple space on the die. Microbumps increase interconnect density marginally, but were still taken up significant area. The size of this interface is dead silicon, which is not cost or performance efficient for the non-stacked products where we utilize the same CCD. With TSVs and hybrid bonding, we can increase the interconnect density by more than 16x to enable the 2 terabytes per second interconnect bandwidth in an extremely small die footprint and still allow for good efficiencies for non-stacked products. Let's take one more look at the elegant engineering feat that our AMD team has achieved. The 3D chiplet architecture has also been carefully engineered to enable the highest bandwidth at the lowest silicon area using direct copper-to-copper hybrid bonding technology, plus through silicon vias for the die-to-die communication. The architecture and the silicon floor plan was also carefully engineered to enable optimized electrical, but also thermal performance. As an example, we designed the 3D 64 megabyte SRAM over the SRAM cells on the CCD to keep thermal density low over just the L3 cache and avoided overlapping on the CCD. We enabled structural silicon for heat escape from the higher density cores or CCDs, illustrating how 3D can be done in a thermally friendly manner. AMD's 3D architecture is enabled by a novel process called hybrid bonding, which we developed in deep partnership with our foundry partners, leveraging their 3D fabric technologies. Hybrid bonding is fundamentally a two-phase bonding approach. The first phase is where an initial hydrophilic dielectric to dielectric bond is created at room temperature, followed by an annealing step, wherein the activated dangling bonds of the dielectric functional groups are covalently bonded. The second phase is a direct copper-to-copper bond enabled by the same or a subsequent anneal step, and the copper-to-copper bonds are formed by solid-state diffusion. Now we compare AMD's copper-based 3D architecture versus the current best-in-class solder-based microbump 3D architectures that's out in the market today. Solder-based microbump technologies with tall through-silicon vias is based on traditional solder-based package technologies and can scale from 50 to 36 microns, maybe a bit lower, and is okay for low bandwidth applications. AMD's 3D chiplet architecture, as shown to scale related to the microbump technology, by contrast, uses silicon fab-like manufacturing methods with back-end of line design rules with TSV-based copper-only interconnects without the presence of any kind of solder. This is a transformational point in industry's advanced packaging journey, where interconnect technologies that were originally developed with solder-based interconnects are now being enabled using silicon fab-based techniques to enable extreme bandwidth interconnect architectures. As a result of the extreme scaling, we're able to achieve more than 3x higher interconnect energy efficiency, more than 15x higher interconnect density, as well as better signal and power performance compared to microbump 3D architectures. This chart shows the interconnect pitch differences between 2D C4 architectures at 130 micron bump pitch, 3D microbump architectures at 50 micron bump pitch, illustrated in blue, and 3D TSV-based interconnects at 9 micron bump pitch, illustrated in orange. Due to this extremely high packing density using TSVs and hybrid bonding, we can achieve more than 3x improved interconnect power related to microbump architectures, providing the best PPAC benefits to enable high-performance computing products. Many of today's games have intense demands for the PC's memory subsystem, and they get much faster when a deep pool of memory is right there on the processor. As we continue to test our 3D chiplet prototype against a long list of games, we are seeing an average improvement of 15% at 1080p resolution. If you step back and think about it, 15% is an entire architectural generation's worth of gaming performance just from the 3D chiplet technology, illustrating the power of advanced packaging technologies. Products based on this technology, Milan-X and a desktop product, has been announced over the last couple of months, and we'll be starting shipping products this quarter. Today's demonstration of the 3D cache stacking over the CPU cores is just the beginning of the 3D journey. The future of 3D stacking is a function of TSV pitch and can spawn many architectural innovations in the future. IP on IP stacking, macro on macro stacking, IP folding and splitting, as well as circuit level slicing. And these are not just pie in the sky concepts, but these are things that we're actually working on for future products. 3D stacking technology progression, along with other advanced packaging technologies, will enable beyond Moore's law scaling this decade and enable complex heterogeneous integration schemes not possible even with monolithic designs. With 2D MCMs, 2.5D silicon interposer, and the breakthrough 3D architectures for chiplet integration, AMD's advanced packaging roadmap continues pushing the bar in interconnect density portfolio to enable high-performance computing products. Combined with our industry-leading interconnect size, our advanced packaging leadership will drive our high-performance computing story forward. With silicon process nodes slowing, advanced packaging innovations are critical to enable the future of compute, as well as developing flexible approaches for multiple product use cases to deliver best-in-class PPAC solutions. And with that, I'd once again like to thank ThoughtWorks for inviting me to present our vision on advanced packaging and the countless AMD team members who have helped move these exciting technologies forward. Thank you once again.
Thank you so much, Dr. Swaminathan. I'm just checking if there are any open questions. Maybe one question from my side. I understand that the 3D architecture and the 3D chiplet architecture is a new milestone, a new type of architecture. How long do you, and I think it's in the beginning, how long do you think will it push out Moore's law to hold still? Or does it need something like very soon?
I need $1 billion to answer that question. The way I look at it is, this is a groundbreaking architecture that is essentially pushing Moore's law in a different dimension, like let's say the third dimension. I think the standard Moore's law, as it's defined purely by silicon scaling, will continue to happen, but it's probably going to not scale as efficiently. The key piece about, it's not about Moore's law anymore, it's about more than Moore. What else can you integrate? How do we mix and match different pieces of silicon to provide unique architectures as what is going to drive the industry forward? So I think in that sense, I would personally stop talking about Moore's law, but also about how do I make the better products moving forward?
Right. And maybe how How do you, I'm not sure if you were able to follow all the other talks of today, but we had different approaches, how to scale even further. So we talked about compiling applications down to domain specific architectures, or how to be more focused around memory. Are these combination of what you were describing, or can we even combine those approaches?
Absolutely, that's a good question. So none of these innovations are going to exist in silo. I think for so long, the industry has been focused on silicon and fab process scaling as the only metric. I think that has broken down completely over the last 5 years or a decade, depending on who you talk to. And to me, this advanced packaging technologies, and we just talked about one of them. In my team, we are innovating on multiple levels of advanced packaging integrations. And we'll start talking more about this in the future meetings. But I think it provides a significantly wide portfolio to be able to mix and match various architectures that some people have talked about. I think the previous talk was about processor and memory. You could either design it as a monolithic piece, or you can disaggregate it like we did and put it together with different interconnect or advanced packaging architectures. So and by the way, we are also investigating processor and memory very heavily. So multiple architectures can be developed independently, but I think moving forward, the advanced packaging platforms are what is going to bring them together, not monolithic silicon or fab process scaling.
Right. Interesting. Yeah. Just another question came up. Could we expect multi-layer heterogeneous stacking in 3D packaging?
Multi-layer heterogeneous packaging in 3D stacking. Maybe you can elaborate on that question a little bit more, because there are multiple levels to that question.
Right. Harshal, you want to quickly explain?
Yeah. So this is basically when you showed us that there is a possibility of adding or stacking, different, say SRAM on top of processing elements. I was wondering if we could have different types of heterogeneous layering, like GPUs as well as SRAM and so on, and one above another. So it could lead to say 2 or 3 or 4 layers of stacking. I don't know if it is really possible.
Yeah, anything is possible, right? We have actually shown multiple level stacking in our prototype experiments. The real question is it's not a question of can we do it. I think the technologies exist that we can do it. The question is, should we do it? If you look at a concept like SRAM on CPU, like we talked about, so just the stacking process itself, we can do it, right? What are the other downstream implications? What are the thermal impacts? What are the electrical impacts? What are the known good die impacts? There's a lot of challenges that we have to do. So based on the specific product use case, we make these choices on a very product specific basis. If I stack CPU on CPU, the first obvious question is, can I efficiently get thermals away from the bottommost stack? And if I have a high power logic right on top of another high power logic, is it the best way to extract my thermals out of it? Those are questions we address on a daily basis based on products. But the philosophical answer to your question is we can stack multiple layers, no questions about it. Memory on memory. I mean, people are doing 8, 12 high stacks of memory using traditional solder-based technologies. And I think Samsung and other companies are also investigating hybrid bonded-based memory stacks. So you can do multiple levels. So for unique product applications, we can do multiple level stacks. That's my long but short answer. Does that answer your question, Harshal?
Yeah, definitely. Thank you, Dr. Raja.
Sure. Thank you. Yes.